Hello, thank you for taking interest in our work entitled Probabilistic Topometric Localization with Off-Map Awareness. This was published in Robotics and Automation Letters. My name is Ming. I'm a PhD researcher at the QT Center for Robotics. This work was done in collaboration with Tobias Fischer, Niko Sunderhauf, and Michael Milford, all of whom are part of the center. So what's the motivation of our work? We wish to enable off-map awareness for visual place recognition-based localization systems. What does that mean? Let's be a little bit more specific. So if we were to take visual place recognition and use this to build a localization system naively, we would do so by using top one retrieval. So given a query image, which we wish to position, we find the best matching image in a reference database of images. And then positioning of a query image can be metric. So if all these reference images have an associated pose, we can inherit that pose, or it can be purely topological. So each reference image is associated with a unique place. So we can see this in the bottom. This figure was taken from Revard et al. 2019, where we have query images on the left, and we have a set of reference images to the right. And we wish to find the best match within this database. So how do we do this? Well, recent state-of-the-art methods are based on this idea of global image descriptors. So these global descriptor methods encode images into a low-dimensional vector space. And then we match by taking these vector representations, we perform pairwise Euclidean distance computations, and we take the minimum Euclidean distance reference image as the best match. So methods such as NetVLAD, APGEM, DenseVLAD, they all utilize this approach for place recognition. And why do we want to do this? Well, empirically, these methods seem to demonstrate very high robustness to viewpoint and appearance changes. And also there's scalability arguments around favorable inference time, so computing Euclidean distance, as well as storage arguments. And so we can see this in the top right. So the top right, this figure was taken from the NetVLAD paper, where you take an image and you encode this into a fixed dimensional vector representation, which we then use for retrieval. Now, methods are evaluated using information retrieval metrics. So for example, precision recall curves and area under the curve. We can see this in the bottom right-hand corner. We have an example of a precision recall curve. This was taken from a survey paper by Garg et al. Sorry, that should be 2021, not 2019, apologies. Now, what's the motivation for our work? Well, top one matching performance has improved. There's a big focus on improving invariance to viewpoint and appearance change. So performance is very impressive at the moment, but there's limited spatial awareness for downstream navigation tasks. And what I mean by that specifically is, well, a lot of these current methods, when you evaluate them, they assume the query image has an associated reference match. That's an implicit assumption in a lot of these models. And so what happens if the query image is captured not within the map? So existing methods only fail if the retrieved match image is incorrect. But if there is no relevant retrieved image, then this method won't work. So we wish to address this specific limitation in this work. So given a query image or given a sequence of query images, we're doing it this way, we wish to infer whether or not a query image is captured within the map or off the map explicitly. So I want to note that FabMap by Cummins and Newman over a decade ago had a mechanism for this. It was a probabilistic system based on bagged words, and it had an explicit mechanism for predicting whether or not an image was captured within the map. However, this method has limited invariance to appearance change. So we wish to take these global image descriptor methods with strong robustness to appearance and viewpoint change and apply this spatial awareness that FabMap had, and we want to augment that. So we can see this in the image in the right. So I'll just move my face. The blue is the reference traverse. It's moving through the environment and it's taking a right around the bend. With query traverse, the query traverse is following the reference traverse, but then deviates. Instead of going around the bend, it continues on straight. And we wish to handle this particular case. So we handle this case using a discrete method, and we have this off-map probability and this off-map state, which we'll describe soon. But you can see this in the right-hand side of the figure, as the robot leaves the map, the likelihood that the robot is off map increases. And this is the functionality, high-level functionality that we wish to include in our model. So a bit about our approach. So our approach, so we utilize a discrete filtering-based localization system, and this combines visual place recognition with 3DOF odometry. So to describe our discrete filter, we need to describe our discrete state formulation. So we extend the discrete state formulation and filtering formulation from our previous work with a novel off-map state. And this off-map state is key for inferring when the robot is on or off the map. And so a map is represented as a set of images, and these images are sampled at uniform spatial intervals. So we take a traverse, a reference traverse, we sample them every 0.5 meters. And then each image corresponds to a unique place. So places are connected by state transitions. So specifically nearby places due to spatial temporal constraints are connected with possible state transitions. And also places are connected with the off-map state and vice versa. The off-map state can transition back to any of the places. So this allows the robot during the query traverse to move in and out of the map, which is required. So in the data sets that we evaluate on, there are multiple route deviations. So you can see this in the right-hand side. So we also need to describe our motion and measurement models. So we have a probabilistic motion model. We can see that there's a diagram explaining this in the bottom right-hand corner. And we also have a measurement model. So just to note on the state, so with the actual states, the robot can be in any number of places as well as the off-map state. And this represents the possible states for a query image at each time step, right? And in terms of the motion model is conditioned on odometry. So it's conditioned on both the query odometry, so the relative pose information between query images, as well as in the reference map as well. So we have relative pose estimates between the reference images within the map. And this parameterizes the motion model, so this probabilistic motion model. We assume that the odometry is probabilistic, so we assume that the relative poses are given by Gaussian random variables. So for example, we can apply a Kalman filter on IMU data. And this is how we parameterize a motion model. With the measurement model, we use the image retrieval matching scores from VPR. So please see the paper for more details. The top right-hand corner is actually your Bayes network diagram, which I'm blocking at the moment, but this provides the formulation. So what are we actually doing with this filter? Well, this is our inference pipeline. We're tackling this loop closure detection task. So given a query traverse, so we have a set of images, a sequence of images and odometry, we wish to infer the off-map status. So for each image, at each time step in the query traverse, we want to see whether or not it's within the map. And if it's within the map, what is the most likely position? So how do we do this? We apply forward filtering. So we have a filtering framework. So naturally, we would apply forward filtering using the motion and measurement updates. And so what we get at each time step from this is we get a posterior distribution over all states. So we can see this to the right and the top. We can see a posterior distribution over all places. At time equals 0, it's not very confident, but then over time, the robot becomes much more confident as to its position. And we want to utilize the uncertainty in this belief for inference. So the robot only localizes if the posterior belief is sufficiently concentrated around a particular place, if it's above a threshold. If it's not, then we infer that the robot is off map. It's not within the map. Otherwise, it is within the map. Now, I just want to note is we actually picked a discrete filtering formulation over a continuous formulation, like a particle filter, for many reasons. One is discrete filters are topological. We don't need pose estimates for each place, which is beneficial. Discrete methods are very fast, which is also beneficial compared to particle filtering based methods, but also discrete methods can utilize the backward smoothing algorithm. So we find that using the backward smoothing algorithm improves localization performance substantially and beats particle filtering methods by a large margin, as we show in our experiments. So now on to experiments and results. So we use the RobotCar dataset to evaluate our method by Madden et al. So this dataset provides multiple traverses through Oxford using a car fitted with multiple sensing modalities. So we use front-facing cameras and we use visual odometry. Cameras are used to extract global image descriptors for the measurement model. So we use 4 traverses. So 1 reference traverse, the overcast traverse in blue, and we use 4 query traverses. So we use dusk and night. So dusk and night are actually aligned, so there are no root deviations with the reference, but they exhibit substantial appearance change compared to the reference traverse. And the rain and the sun, the red and the purple, illustrate large root deviations. So the query traverses have very large root deviations. So you can see they leave and return to the map multiple times within the map. And this is very challenging for existing systems. So what we really wanted to show here is we wanted to show that where no root deviations are present, our method still works. It doesn't compromise in performance. However, when root deviations are present, we show substantially improved performance. So here's some of the results. We use precision recall curves. So we use a tolerance of 5 meters. So if a query image is successfully, so if the query image infers that it's at a particular place, it's only correct if it's within 5 meters. So we have a very sort of strong tolerance here. And so our proposed method yields substantial performance gains when detours are present. So we can see this in the rain and the sun traverse. So higher and to the right is better. Our method is in the dark solid green line is our best performing method. And what we can see is massive improvements compared to our single image baseline, as well as other comparable filtering based systems. To the left, we see the dusk and the night traverse, so no root deviations, and we show that our method yields very, very strong performance, comparable, if not better than state of the art as well. One thing to note as well is that the dashed line is forward filtering only, whereas the solid line is backward smoothing. So this is showcasing, the gap is showcasing the utility of using backward smoothing. And also we evaluate on this global localization or this wake-up approach. So this was done in our previous work. So with these filtering-based approaches, we can solve this wake-up problem where we initialize the robot with no prior position estimate, and then we let it consume sensor data until it's sufficiently confident as to its position, and then it localizes. And we show that our method also yields very comparable results compared to other methods on this particular task. And this is what we can do with a filtering-based approach. So finally, onto future work. What we really wish to do is in this approach, we had to simplify. We assume that the reference traverse follows a single linear trajectory. We want to extend this to a more general network map topology in future work. And also what we wish to do is, well, we can do this loop closure detection, we can do this data association even when the query traverse leaves the map. So we want to use some of these techniques as a foundation for a multi-session mapping problem, where we can take multiple traverses and we can stitch them together into a topologically consistent map across large-scale appearance change over multiple traverses. Anyways, thank you for listening. If you got this far, and please don't be shy, come and say hello. It'd be very nice to see a friendly face. Thank you for your attention.